Hello everyone, welcome back in the course of Higher Surveying. Today we are in lecture 4 of module 7. In the last 3 lectures we have learned fundamental principles of the laser and how laser can be used to determine the time of flight and distance and so on. So basically we said that we can determine the range over a large distance, say some kilometers, 1 kilometer or so. Using that information, we learned that how to configure various sensors, for example GPS, IMU and laser scanner to acquire the 3D data of the terrain using airborne platform or terrestrial platform. Once we acquire the data in the swath, one flight line is leading to one swath, and swath is the distance perpendicular to the flight line. We have the overlap, so using the information from GPS, that is trajectory of aircraft, and the IMU, that is the roll, pitch and yaw of the aircraft position at different locations on the aircraft trajectory, and the laser scanner data, that is the scan angle and the range for each pulse. We learned how to do geolocation process to georeference the 3D data in one global reference frame. So let us say that we have a LiDAR data which is georeferenced, as well as the data has only random errors, no systematic errors there. And now I can use this data for generating different 3D products. So in this lecture, we are going to talk about how to extract the information from the LiDAR data. So this is lecture 4 on information extraction using LiDAR data. What are the possible products? The data once acquired by the LiDAR and it is georeferenced by direct georeferencing method, then that data represents the surface of Earth in the given area of interest. So if there is a tree, I will have the surface of the tree expressed by the LiDAR data, and I will have the multiple returns also. So I have different layers of the tree. On the other hand, if I have building data, then data is also there of the building site and building rooftops. And similarly, if I have a terrain or open ground, I will have the data of the terrain. And each data is subjected to some random errors, but the data is still a point data. Data is not rectangular grids. Now, what are the possible products that I can make from this data? The first product is digital elevation model, and second product is digital terrain model. Moreover, I can also prepare digital surface model. So what is the difference between the three terms? If I have that data and data is representing the actual surface of the Earth, that includes all the natural as well as man-made structures. For example, tree, buildings and terrain, everything is there. So that is called digital surface model because it is representing the real surface of the Earth. How Earth or the area of interest look like. So DSM is representing that actually. What about the digital elevation model? Digital elevation model is very generic term that we use in order to specify the 3D data in the form of grids. So each grid is having X, Y and Z, where Z is the height of the grid and X and Y is the planimetric position of the center of the grid. So this is what we call DEM, a generic term. What about a DTM? If you consider trees and the buildings, buildings are man-made or artificial structures. However, trees are dynamic structures. In a sense, they grow with time, and so these structures are natural structure. Or maybe if I talk about some kind of small pit of any size, but we know that it is not a part of the natural terrain. So all these features, if I remove from the DSM, then I'll get the DTM, what we call digital terrain model. And what is the importance of DTM? For very large scale study, for example, mega floods like tsunami, we want to have the terrain surface. That is more important, not individual building or individual tree is important. On the other hand, if you look into the urban areas, if they are thickly populated by the buildings, we cannot ignore the buildings. In that case, we need to have the digital surface model. So in those cases, digital surface model is more important than DTM. In this lecture, we are going to talk about building extraction, digital elevation model development and digital terrain model development using LiDAR data. Let us start that what are the features. We have linear features like road, river, railway lines, athletic track, etc. We have vertical features, for example, buildings, that means they are growing more in the vertical direction compared to the horizontal direction. Then we have electric poles, or telephone poles. Then we have overhead high tension electricity wires or lines. Then we have trees also. So these are vertical features. Then we have planimetric features, for example, a plain ground, maybe a building which has less height compared to its horizontal dimensions. Then we have grassland and so on. Okay, what are the hybrid features? Hybrid features means the places which has both vertical as well as horizontal features. For example, stadium. Stadium has very high, huge building. At the same time, it has very large ground. Then we have university campus. Such things are classified in the hybrid features. So using LiDAR data, we want to look into the various feature extraction as well as digital elevation model and digital terrain model extraction. So now in case of LiDAR, we know that it is a point data and also it is not regularly placed or it is not uniformly placed. If I want to prepare the digital elevation model or digital terrain model using LiDAR data, I need to consider some algorithms. So there are two types of algorithms. The first is the raster data based algorithms and the second type is vector data based algorithms. We can use any of these algorithms to create the digital elevation model. All these algorithms are in the category of topological algorithms, and topology is the relationship of one point with its neighborhood. Let's talk about the raster based algorithms for the digital elevation model preparation using LiDAR data. Now we have to create the LiDAR image. LiDAR image is written as Z is equal to L indicating LiDAR and P comma L, where P is point number and L is line number. So which line I am referring to and which point in that line I am referring to. What is the elevation of the point? Before that, we should also know one thing, that finally I will get X, Y, Z 3D coordinates. Then we have intensity information, and then we have the return number. In case of multiple return, I have maybe second return, third return and so on. So we have this data with us and I want to utilize this data only, using the first return only, because we are working on the top of the structure, for example building top or maybe tree top or maybe terrain top. We want to use this XYZ data which is 3D, and we want to develop the various products like digital elevation model or DTM, or maybe we want to extract the building information. So let us express LiDAR data in an image form. So what does it mean? Let us say this is area of interest and this is the data given, which is randomly distributed LiDAR data. Let us develop LiDAR image and divide this image into the grids like this. So these are square grids. So this particular pixel, for example here, it is represented by Z is equal to LPL, which is written here. What is that? Z is the elevation of the grid. You can understand the similarity between the digital elevation model from satellite image. How do we express it? Z is equal to function of xy. Sometimes we also write the function of row and column. So instead of this, I am representing this location by P and L. Now I want to find out what is the value of the Z at a given location PL. That means what is the value of Z for this pixel here. What are the methods that I can use in order to extract this information of Z using the LiDAR data? So that once I have filled the Z data for all the grids, I will have the digital elevation model. So we have two methods. One is the general method and one is proximity method. Proximity methods are basically coming from the photogrammetry or image processing. Before going into these methods, we have to have grid size defined. So first of all, we define grid size. This is grid size here and this is the grid size in the y direction here, and let us call it delta L and let us call this delta P. Delta P and delta L are equal, so I am having a square grid and this is given by the 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 × 3 area of interest divided by number of lidar points. I have calculated the delta p value and delta L value, and then I have developed this grid and overlaid on the given lidar data. The next step is define the neighborhood, so that we can use either proximity method or general method. First talk about the proximity method. There are three proximity methods. One is nearest neighbor, second is bilinear interpolation. We have done this thing in the photogrammetry, and then bicubic interpolation. We have already discussed about bilinear interpolation in photogrammetry. I am only going to discuss about the nearest neighbor here. So, let us see, this is grid. This is PL. I want to fill the Z value. What is the Z? Given LPL. In case of nearest neighbor method, I will consider the nearest neighbor or the point which is located nearest to the PL location. So, PL is central location here, and let us say there are some points located here randomly. So, these are all lidar points, they are falling in these grids. I will take the points which are around the PL and try to find out the Euclidean distance from this point, this point, this point, and so on, like this point. And then the point which is nearest to the PL location, we will assign Z value of point to this grid. So, we have seen that we have defined the nearest neighbor and we have assigned the Z value. So, remaining two methods like bilinear interpolation and bicubic interpolation, you can find it yourself. Now, we have the general method. So, in case of general method, we take the weighted average of all lidar points which are in neighborhood. Now, how to calculate the Z value? And that is the weight I Zi divided by Wi sigma. So, that is weighted average. Of Zi values of lidar points that are in neighborhood, and we have already defined the neighborhood. So, how to define the weight? So, weight is inversely proportional to the Euclidean distance square, the Euclidean distance between the point L and Ti. So, once we define that I number of points or n number of points which I am indexing by the I one by one, Euclidean distance is this much, and if I make the square of this distance, so this is weight. That means, higher the distance from the candidate pixel PL to a point Ti, I will give less weightage to that, and finally, by this way I will calculate the weighted average. So, this is the general method. So, these two methods are the raster based methods, where we have a grid and we want to fill the data on the grid. So, let us say by this method we have prepared a digital elevation model. What about the other method? The lidar data is a point data. So, I can develop some vector based algorithms also. Let us talk about the vector based algorithms. So, vector based algorithms are based on the Delaunay triangulation method. So, let us look into the Delaunay triangulation. Let us see, there are few points, these are lidar points. So, each point is representing lidar point. Here, using these points, I am going to develop triangles and triangulation scheme, where each triangle will represent certain area. So, we have triangular, irregular network. So, we have 2D triangulation scheme, we have 3D triangulation also. This is called the tetrahedron. Now, how to develop this triangulation scheme or tin? A method is Delaunay triangulation. First, take any 3 points and develop a triangle. Now, fit a circumscribing circle passing through these 3 points of the triangle like this. So, now you realize that within this circle there is another point falling here, you can see here. So, that is not an appropriate condition for this Delaunay triangulation. So, what we will do, if we develop a triangle, then there will be 2 triangles in one circle that we do not want. So, what will you do now? We will swap the diagonals of the 2 triangles, or we can say quadrangle. I will remove this diagonal and I will develop this diagonal, and by this way I will create 2 triangles. So, let us see, I remove the diagonal and I created another diagonal, and that is what we call the diagonal swapping. So, you learned that how to do the swapping of diagonal. Let us fit the circle again to this triangle, the purple triangle and the yellow triangle. So, like this, now I can see in each of the circle there is no 4th point lying. Let us take one more point. So, let us say this point, I have developed a triangle here and again fit a circle like this, and again we can see that this point is falling inside. Again we have to do the diagonal swapping. This is new triangle and 2 triangles are falling in one circle. So, what will I do? I will remove this diagonal and I will create this diagonal like this and like this. So, I got 2 triangles from the quadrangle. Let us fit the circles again for this green triangle and the another triangle. So, I get again 2 circles and each circle contains only 3 points on its circumference. So, this is the process called Delaunay triangulation by diagonal swapping method. So, let us consider 2 more points. So, let us develop this way and try to fit a circle through these 3 points. Now, there is no point which is falling inside the circle. So, that is acceptable triangle. What about the last point? The last point is this, that I will connect, and this is the triangular irregular network using diagonal swapping method. If I number these triangles 1, 2, 3, 4, 5, 6 and 7. So, how to store this data, or how the triangular irregular network store the data? If I talk about the triangle, so this is triangle number here, put all the triangle numbers here, for example, let us say 1, 2, 3 and so on. Now, the next is vertices information. So, that means there are 3 vertices for each triangle. So, let us call these vertices as A, B, C, D, E, F, G, H. So, we have numbered all the vertices by A, B, C, D. For triangle number 1, I can see here that A, B and C are the 3 vertices. And what about the neighboring triangles? So, neighboring triangles are triangle number 6 and 2. So, let us consider the triangle number 2 now. So, for triangle number 2, we have vertices A, H and C. And what are the neighboring triangles? Neighboring triangles are 1 and 3. Similarly, you can fill it for 3 and 4 also yourself. Let us consider the triangle number 5. So, what are the vertices here? C, F and D. And what are the neighboring triangles? There are 3 neighboring triangles, 4, 6, 7. So, now we can understand that this is the triangular irregular network and this is the data structure of the tin. That means how these data are stored in a memory or computer. I want to extract the information of, let's say, certain triangle, for example triangle number 4 or triangle number 5. So I know that triangle number 5 consists of 3 vertices and triangle number 5 has 3 neighboring triangles. We already know that these vertices have some coordinate, for example that A, B, C and so on. A point has XA, YA, ZA. Similarly, this will have XB, YB, ZB and so on. So, using this information, I can find out any information that is to be interpolated from this data set or from this data structure. Each triangle is having some Z value, so it is representing some kind of terrain. You can see here that tin method is representing the terrain more faithfully because they are considering the real points and they are developing the terrain surface. Now, what about the 3D tetrahedron or 3D triangulation? In this case, I will have triangles which is in 3D in nature. That means there are 3 points, 1 point, 2 point and 3 point. So, I am developing a triangle like this, and similarly I will connect these triangles and I will represent the complete surface as it is on the surface of earth. And so, I want to find out the Z value within the triangle. I will take the X and Y value and I will put this X and Y value, and then I will try to interpolate using the 3 vertices of the 3D triangle, and I will find out the Z value which is lying on the plane of a triangle. So, there are 2 ways of doing it. Now, I am representing the terrain by 2 ways. One is raster based, that is digital elevation model, or I can also represent it by the vector based triangular irregular network or TIN. Question is, how can I extract the buildings as well as digital terrain model? So, first consider the digital terrain model. In order to develop the digital terrain model from LIDAR data, we have vector based algorithm, raster based algorithm, as well as we have some 2 or more operations. One is called the replacement and one is called the culling operation. They are in addition to digital elevation model or to vector model, that is TIN model. So, we are going to implement this replacement and culling operation also after developing DEM or maybe TIN, so that I can find out the terrain or I can extract the terrain information. So, there are 4 methods we generally employ for DTM generation. So, first method is global thresholding method. So, in this method we decide one global threshold on Z values. The purpose is, above this global threshold, whatever points are falling, I will remove those points from digital elevation model or maybe TIN model. If I consider it very appropriately, in one attempt it will remove all the points which are belonging to tree or building, or then we will have the real terrain that was originally there when there was no tree and there was no buildings were constructed. So, I have the global thresholding method. If there is a point Ti as given by Xi, Yi, Zi, I can create the DTM as point Ti. That means point Ti will belong to the DTM given Ti is in the space and Zi is less than or equal to certain threshold. The problem is, the moment we decide the global threshold, it has to come from some logic, and this logic is generally not appropriate because for tree or building or any structure, I cannot have a global threshold. The slopy roof of a building like this, it's very common in Guwahati. So, wherever we feel that there is snowfall or maybe rainfall or in excess, such structures are very common. Now, if I have some data and if I define global threshold like this data will be removed which is above this global threshold, and this data will be part of the DTM, which is not true. So, that is the problem is in the global thresholding algorithm. And now, we define new method called local minimum algorithm. which is an improvement over the global thresholding algorithm. Let us assume that again point Ti is given, which is xy, yi, zi. According to the local minimum algorithm, we replace all the points by minimum elevation. So, how to find out this minimum elevation? So, first define the neighborhood. So, let us see that the neighborhood is point Ti given location Tj. All these points are LIDAR tuple. So, I am saying that the point TEI is neighborhood at a given location Tj or for the given point Tj. So, let us say the point Ti given the Tj point is in the sample space or my LIDAR data, or I can say yes, the complete sample space, and the Euclidean distance between the Ti and Tj is less than some threshold. So, this is the way we define it. So, this minimum elevation is defined on a neighborhood, and we already learned that how to define a neighborhood. So, let us see dTm is equal to Ti dash. I am writing, since I am replacing the points, so I am writing now Ti dash, not the Ti, given that Ti dash is in the space and Zi dash is equal to the minimum of Zj, where all the Tj are in the neighborhood of I point. So, this is the way we write algorithm for dTm. So, this is the way we replace elevation of point by Ti dash, given that the Zi dash is equal to the minimum of all the Zj, where Zj belongs to Tj and Tj is in the neighborhood of the Ti. That means, using the neighborhood information, I am finding out minimum around a point Ti and I am replacing the Z values of Ti using some neighborhood information. So, that is local minimum algorithm. So, now I can see that I am doing some operation not by global method, I am defining a neighborhood around the point, and then using that particular data set only, I am replacing the candidate pixel or candidate point by the local minimum. What about the problems here? Let us say there is a situation where terrain is like this, there is a small valley because data points are here, and this valley is not part of dTm, it is a small pit. What will happen here? If I define a neighborhood like this is Z minimum of the neighborhood. If I will get dTm like this, where this is Z minimum. So, this structure becomes wider like this, and that is the problem. This is not 2 dTm. So, to avoid such situation, we need to improvise the algorithm. So, we have new algorithm called median filter algorithm. What is the median filter? We have the median term from the statistics. So, what we will do, we will find out the median of all this point, and that point will be somewhere here, because we know that this data is very less in numbers. So, if I take the median by arranging in descending order or ascending order, I will find out some point maybe here or maybe here. Now, if I replace all the points by this median, what will happen? For this kind of terrain where these are points, dTm will be like this. That means, I have avoided this complete part, which I know that is not a very true. So, this is dTm. What is the problem with this median filter? Let us consider a situation, say there is a small valley here, and then we have lot of trees here, and trees are surrounding this small area, and I have data over there, all this thing. Here also I have terrain data, here also. If I take the median of such data set, I will get some median at the top of the tree. Now, instead of getting this terrain, I will get this kind of terrain where this is tree height. So, this is not DTM, this is wrong DTM. So, this is the correct DTM. So, these kind of problems are there in the median filter algorithm. Even we take mode, we will face the same problem. To avoid all these situations, we develop some more algorithm like slope based algorithm. What is slope based algorithm? Let us say that if there is a neighborhood like this and I have a point Ti here and there is a, let us say, Euclidean distance here with another point called Tj. So, this is range R or neighborhood. So, now if I calculate the slope between Ti and Tj, that will be tan inverse of Zi minus Zj divided by Euclidean distance between the Ti, Tj, and we are finding out the Euclidean distance on xy only. So, this is slope here between the two 3D points here, and remember this distance is Euclidean distance on the 2D plane xy only. So, I am determining the slope. Moreover, if I consider slope like this, so all the slopes are negative, let us put Zj minus Zi. So, if I consider positive slope like this. So, now this is the algorithm which are called slope based algorithms. We can see that we have written these algorithms for DTM extraction using the vector data. I can also write these things in the raster. These are the methods which are generally used for the digital terrain model development. What about the third aspect, that is the building information extraction? So, let us look into those also now. We have some building representation that we should first understand. LOD0 is level of detail. LOD0 is the building with the simple model. Suppose if I have the building like this and I am representing it by the edges. So, this is the LOD0. What is LOD1? That level of detail 1. If I have the slopy roofs and I am representing them in building model, then it is called the LOD1. What about the LOD2? If I have some architectural details, for example, this LOD1, on top of that if I have some architectural details also like this, there is a window here, this window also represented in building model, then it is called LOD2, and the LOD3 is the LOD2 plus texture information or the color information of the building surface. So, according to the level of detail, I need to decide which algorithm I should use or which algorithm I should develop. So, the ultimate purpose is I want to present building in either of these form. So, then I can characterize that what is the quality or what are the level of details available using the LiDAR data that I extracted. The building extraction methods are categorized in two classes. The class 1 method uses only the LiDAR data, and class 2 method use both LiDAR and the ancillary data. Ancillary data means any additional data, for example, texture information or the image data or maybe thermal image data. Any additional information other than the LiDAR data is called ancillary data. So, if I use the ancillary data along with the LiDAR data, the method will be categorized in the class 2 method. Class 2 methods are more efficient in terms of extracting the building because we have some additional information also. So, here we are limiting to class 1 algorithms only. In the class 1 algorithms, now we are going to consider the 3 algorithms: thresholding algorithm, horizontal profiling, and the least squares fitting of the planes. So, let us consider each one by one. So, again, global thresholding algorithm. First, draw a plane at z is equal to h, this threshold. Then next we project all the points above z equal to h on that plane. We convert the data on plane in binary image. If I have an image plane like this and data is falling like this, which are belonging to building, something like this, there is another building like this, so all these data points are there. Now divide complete planes into the grids, and if there is a radar point in a certain grid, I will call that grid as 1. So, this is 1, this is 0, this is 1, this is 0, this is 0, 0, 0, 0, 0 and so on, 1 here, 1 here, 1 here, 1 here, 1 here, 1 here. Filled pixel belongs to the building. This is building here. So, let us say there is line here, right. So, I got this building. So, this is the way I extracted building. Similarly, I can extract here this building easily. You can see here all the rest of the values are 0 here, and all these values are 0 now. So, this is the way I have extracted two buildings here. So, that is what global thresholding method. The first thing is we can use image processing the way I shown you on the binary image, and there we can consider the height variance also. What is height variance? If I consider the height of the building and buildings are flat, flat buildings having the same heights will have minimum variance of the height, and as a result I can say for this particular area which is building, I will have minimum height variance. So, I will collect those height variance value wherever height variance is minimum is building top. So, now I can use either this method or this method to extract the building shapes. There is a problem because we have global thresholding here, and that is also defined manually by judgment. There could be possibility I can lose the data of slopy roof. So, if the global threshold is like this, I will lose the slopy roof here, and that is not desired. Okay, I would like to tell you one thing in here. When we calculate the height variance, you should know that for the flat roofs, we have minimum variance. For the trees, we have maximum height variance. Then what about the slopy roof? We have some moderate, that means in between the maximum and the minimum value. So, we should understand this information. So, in such cases it fails. So, we devise horizontal slicing method. So, let us see, I have some data. For example, there is a tree like this and there is a building. And I have data all along surface of the tree. Here I have data here, similarly here, and I have data on the top of the building, data on the sides also. Now, you can see here that if I do the horizontal slicing of this data like this, they are planes. So, let us call Z is equal to H1, Z is equal to H2, Z is equal to H3 and so on, Z is equal to H4. Now, I consider between these two thresholds or between these two slices whatever data is there. For a tree, we have this data, and for a building we do not have any data. Now, what about this band? This band is also having some data for the tree, but we do not have any data for the building because all building data are here. I will find out the building shapes for the each plane or the shape of the structure for each plane, for this plane also, this plane also, this plane also, this plane also, using the same method what we have done. Each plane will have certain shape of the trees as well as buildings. Now, if I consider all 4 bands or 5 bands or n number of bands, and I try to find out the CGs of the points or of the structure, maybe tree and building so on, in each band I will find out the same CG for the building, because building CGs does not vary much. But in case of tree, since trees have varying shapes, the CG will keep on shifting from different planes. Looking at the changes in the CG locations, I can say that this is tree structure, so remove it from the data, and that is building structure, accept it. So that is what we call the horizontal slicing method here. I hope that you can appreciate these methods now. The third one is planar surface method. For the given data, try to fit the planes. Mathematically we write plus d equal to 0. So now you can see that z is equal to minus d minus ax minus by upon c, or I can write here minus, let us say, c dash minus a dash x plus b dash y. So I can write z is equal to c dash plus a dash x plus b dash y, where c dash is equal to minus c upon d, a dash is equal to minus a upon d, and b dash is equal to minus b upon d here. I will use the method of least squares, and that is observed value plus I will say that there is some error here, and now I am fitting a plane c dash plus a dash x plus b dash y through the given points. So I have xi, yi. So let us say if there is a rooftop like this, and I have some data here and which has some errors, and there is another rooftop here. When I fit a plane through these points, I will get what the values of a, c dash and b dash. Similarly, if I have some data over there and if I fit a plane, that is plane 2, I will have the fitted plane like this. This is fitted plane and this is fitted plane here. Now, if I intersect two fitted planes, I can reconstruct a building, and experimentally it is proven that using the least squares method, we can also detect the edges of the buildings very efficiently, which originally we cannot extract from the given LIDAR data, because LIDAR data is maybe here and it could be here also. If I fit these lines or the planes, I can extract these edges very nicely. So this is the approach of the planar surface method. So today we have learned some preliminary methods that are used for LIDAR data processing in order to extract the information for various purposes. We have learned how to extract digital elevation model, digital terrain model information, and we also learned how to extract the building information. We finish this lecture here, and we will meet in the next module, module 8 on radar. Thank you very much.